Good day, everyone. Welcome to our lecture for today. Our focus of our session for today is to recall what we have discussed, things about derivatives. So let's recall the major theorems, the figures that you have seen in one of my presentations. And this time we have some student response questions. Okay. All right. For our reference, let us re-examine our course outline contents. So for today's lecture, we're going to focus on this CO2, right? This is the course objective number 2. So the main purpose is to expose you once again to this concept class. So the definition about the derivatives, finding the derivatives of given functions, then the differentiability of a given function, and the interval for which it is differentiable, and the points where its derivative does not exist. Then we will also interpret derivatives geometrically, and we will use the concept of derivative to determine the slope of a curve of a given point. So if we cannot make it this time for this part, then we'll do it in the next video. Right, so the focus of this lecture is on the uh, part 4. It's about the derivative, notion of derivative, definition, determination of the derivatives by increments. Then we have the differentiation rules. And the next is about the slope, the definition of slope as the derivative of function, and determination of the slope of a curve at a given point. So also for this part, if you'll not make it this time, we'll do it in the next video. Okay? Alright, we'll start with this part here. Okay, so let's focus our attention to this graph. So we have here a graph of the function y equal to f of x. So look at this color blue. So graph of the function in color blue. So y equal to f of x. So you have noticed here that there are 2 points on this graph. We have point P. So point P has the coordinates x sub 0 and also f sub x sub 0. So if you can still remember in our previous lecture, so we say that a point is composed of 2 components. That is the abscissa. Abscissa is the distance of the point from the y-axis. So this is what we call abscissa. In this case, our abscissa here is the x sub 0. X sub 0 is the distance from the y-axis towards this point. From the y-axis towards this point, which is equal to this one. And the ordinate is the height of the point from the x-axis, and that is equivalent to f sub x sub 0. This is the value of the function at x equal to x sub 0. Okay, so we have this point, and another point is q. So q is also a point, so it is also comprised of 2 components. That is the abscissa, or the x value, or the distance from the y-axis towards that point, which we call x. So this is our x. This x here is the distance from the y-axis towards this, which is also equivalent to this one. Now, from the y-axis towards that point Q. Alright, then the ordinate, the vertical part of this point, is the distance from the x-axis towards that point. Okay, now if you can still remember in our previous discussion, we have what we call secant line. So what is the secant line? Secant line is the line that intersect the curve or the function at 2 points, at least at 2 points. So in this case, this line We call it secant line. This is the line that intersect at this point, at point P, and also at point Q. All right. So if you look at this distance, no, the horizontal distance of P to Q, so this one. So this is actually the difference of the distances referring to the y-axis. So we know that the distance from the y-axis towards that point Q is what we call x, okay, and the distance from this point from the y-axis to this point P, we have x sub 0. So the difference between these two distances, x minus x sub 0, this is the horizontal distance of this point P and point Q. All right, and we also have the vertical distance between the 2 points. So this is the vertical distance between 2 points. So this is the difference between the ordinates of the 2 points. So the ordinate of this point Q is uh, f sub x. All right, this is the ordinate f sub x. So this is the distance from the y-axis towards that point. This one, y-axis to point Q. This is our f sub x. And for point P, that is f sub x sub 0. So if you look at this distance, is the vertical distance. This is the difference, actually, the difference between the distance f sub x and the distance f sub x sub 0 referring from the x-axis. So we have f sub x minus f sub x sub 0. Okay, now if we are going to move this point Q along this curve going to the left, or if we are going to trace this curve, okay, from this point Q going to point P, so what will happen is that our secant line will move towards the tangent line, right? For example, if the point is here, so we see that the secant line now is this line, okay, and okay, I'll draw the, I'll show you the point. Now, for example, if we move this point Q here, so what will happen is that our secant line will be something like this, right? And as you move this point closer to point P, so what will happen to our secant line? So our secant line moves closer and closer to the tangent line. And as point Q approaches, to P, what will happen to our secant line? Our secant line will approach to tangent line. All right. Okay, so I hope you get that idea, class. And you see, as you move this point along this curve towards P, uh, what will happen to our x? X is the distance from the y-axis towards this point Q. This x will shrink. No, it will move closer and closer to x sub 0, right? So we have this definition. We already have mentioned this before, that suppose that x sub 0 is in the domain of the function f, the tangent line to the curve y equal to f of x at point P with the coordinates x sub 0 and f sub x sub 0 is the line with the equation given in this form: y minus f sub x sub 0 equal to m. M, this is the slope, no, the slope of the tangent line times x minus x sub 0. So where m here, if you solve m, from we use our algebra here to manipulate this given equation and solve for m. So we have m equal to the limit of the function f of x minus f sub x sub 0 divided by x minus x sub 0. So this is true provided that the limit exists. Okay, in other words, you can use this formula now to find the slope of the tangent line provided that as x approaches to x sub 0, the limit exists. Okay, so for simplicity, we'll also call this the tangent line to the function y equal to f of x at x equal to 0. Alright, so that's our definition 2.1.1. So because from our reference, this is taken from chapter 2. 2 there stands for chapter 2, and point 1, item number 1, point 1. Okay, so we have here another scenario. Now this is related to the previous graph, but here we use instead of x, we use the increment h. Means that the distance between the horizontal distance between p and q. There is the horizontal distance. We call it h. So again, our p has the coordinates x sub 0 and f sub x sub 0, and q is this time our q has the coordinates for the x part, the abscissa, we have x sub 0 plus h. Okay, we just add, no, this total distance from the y-axis towards that point q is just the total distance. This is x sub 0, then plus h. So we have x plus h sub 0, x sub 0 plus h. So this is the horizontal component of the point q, and the vertical component of point q is the value of the function at this point, which is just substitute the value of x sub 0 plus h to the given function, and you have this, the vertical component. And now difference. Now if you look at the distance between the vertical distance between p and q, this one, which is equivalent to this one here. So this is just the difference, the height of this point, which is f sub x sub 0 plus h, this one here, is the height of this point q, minus the height of this point p. So in other words, this is the difference between the two heights. Heights of q from the x-axis, and height of p from the x-axis also. So that's why we have here the difference. Again, we have here the secant line. Alright, and we have our tangent line here. Now as we move this point q closer and closer to point p, we see that the secant line moves closer and closer to tangent line, and the limit of this is the tangent line. So it means that as point q reaches at this point or approaches at point p, then secant line approaches. So the limit of the secant line, in other words, the limit of point q is point p, and the limit of the secant line is the tangent line. So as q approaches to p, then the secant line approaches to tangent line. Alright? So we have here another definition which is related to the previous one. So the function f prime of x defined by the formula f prime of x equal to the limit of f of x of x plus h minus f of x divided by h as h approaches to 0. So this is what we call the derivative of f, meaning the derivative of function f with respect to x. So the domain of f prime, meaning the derivative of the function, consists of all x in the domain of f for which the limit exists. Okay, so I hope you can see the difference between the two definition class. Now we have here the steps in finding the equation of the tangent line to the given function y equal to f of x at x equal to x sub 0. X sub 0 here is any value. We can have x equal to 0, x equal to negative numbers, or positive numbers. So the first step is to evaluate the f sub x sub 0. Okay, it means that you have to find the value of the function at x equal to x sub 0. So what is the value of that function at that point, at that value of x? So the point of tangency, we call it the point of tangency, which has the coordinates or contains the coordinate x sub 0 and f sub x sub 0. Then after that, you move to step 2. So you have to find the derivative of the function of x, and evaluate the f prime of x sub 0. It means that you have to find the value of f prime when you substitute the value of x at that point, the point of tangency, which is the slope of the line or slope of the tangent line. Then after that, you substitute the value of the slope m and the point with the coordinates x sub 0 and f sub x sub 0 into the Points law form. So our Points law form is given by this equation y minus f sub x sub 0 equal to y f prime of x sub 0 times x minus x sub 0. So in analytic geometry class, this is the same as when you say y minus y1. So in our analytic geometry, we use this formula for the Points law form equal to m times x minus x1. Okay, so they're just the same. If you can still remember this from our analytic geometry. Okay, m here in our discussion, in this case, we have f prime of x sub 0, that is the slope. Okay, that is the slope of the tangent line. Or equivalently, solving for y here in terms of the other items, you just move this to the other side. So that's why we have only y on the left side and the rest on the other side. So we can call this as our equation number 3. So when you find the equation of the tangent line to this function y equal to f of x at x equal to 0, you just follow these steps. Okay. Now we have here another definition. We call it definition 2.2.2. So a function f is said to be differentiable at x sub 0 if f prime of x sub 0 equal to the limit of the function of x sub 0 plus h minus f sub x sub 0 divided by h as h approaches to 0 exist. So if we know that the derivative of the function exists as h approaches to 0, if you refer to the graph, the secant graph that we have seen a while ago. So if it exists, so therefore, so a function is said to be differentiable at x sub 0. So we can use this, but there's a condition that so the function is differentiable at x sub 0. So it means that it's continuous at the point where the coordinate has x sub 0, or where the x sub 0 is located. So if the function f is differentiable at each point of the open interval, shall we say a b, interval a b, open interval, parenthesis class means the interval is open, so including all values within a to b but excluding a and b, then we say that it is differentiable on ab, on this open interval ab. And similarly for open intervals of the form a, then positive infinity means from the value a towards the positive infinity, but excluding them, no? The a and the positive infinity, as well as the negative infinity, the open interval negative infinity to b, and negative infinity to positive infinity, open interval from negative infinity to positive infinity. So in the last case, meaning in this case, we say that f is differentiable everywhere. All right, so differentiable everywhere. Okay, now we have here some illustration class, and later on we have to magnify this to explain more in details. So we have here a graph or a function given in this graph, function y equal to f of x. So this is the representation of this function. Okay, so at this point we have here our x sub 0, meaning the coordinate, the abscissa of this point is x sub 0. So we call it the corner point. Alright, so in the other illustration, we have y equal to f of x, but we have this kind of graph. Alright, and then we have here this point, okay, where our x sub 0 is located. So this is what we call the point of vertical tangency. So it means that this curve changes, this curve concave upward, and it changes concavity. Don't be bothered with the term class concavity. I will explain that later on. So can changes concavity downward. So initially concave upward, and then changes concavity downward. So this is the point of inflection. So we this time we will call this as the point of vertical tangency. Okay, so remember the term point of vertical tangency. We'll use that concept later on. Now, if we are going to expand or magnify this graph, if you look at this in the magnifying glass, so we can see this kind of graph. So assuming that our point, let's call this point here as our point P. Okay, let's call this point P. Right, and then assuming that we have another point here, point Q. So point Q, we have here x, the horizontal component of this point, we have x, and our point P has the horizontal component x sub 0. And as we move, no, if we move from left to x sub 0, it means that if we trace this graph, so we move the point Q, okay, so assuming values for x, our values for x is increasing from the left going to x sub 0. Okay, so our x approaches to x sub 0 from the left. Okay, so we're considering the left part of the curve tracing towards point P. Then our value of x approaches to x sub 0. In similar way, if we have this q moving from right to x sub 0, or moving towards P, then our x values here, x component will go down, but as it goes down in values, our q, our function is increasing. All right, and it approaches to point P. Okay, so in this case, if you look at this arrow class, it means our x approaches to x sub 0. Now from the left here, we have our x approaches x sub 0 from the right. So here our further explanation. Now using this secant graph, now this one. So the first graph here is the magnified version of this one. So what I am emphasizing here is the tracing of the curve, towards P from point Q, from both directions, from the left and also from the right. Now, considering this secant graph here, and if we magnify that one, so we have it here. So as this point, as we move, considering this upper part where the graph is concaving downward, as we move point point Q towards point P. By the way, this is our secant line. Remember, this is our secant line. So as we move point Q to this point, so our secant line is moving also, right? So as you move this point Q farther to this point, so you see the secant line is moving also towards this direction. Okay, so we can say that the slope, the slope of this secant line tends towards positive infinity. Why? Because it reaches the limit here is the vertical point of tangency. So the point of vertical tangency. Okay, so it tends to move towards this point, the point of vertical tangency. Okay, so slope tends towards positive infinity. On the other hand, if you look at the part where uh, this one concave, actually this is just the same as related to this one, but this is concave upward. Okay, but assuming our q is from here, and then as we move our x, I mean if we move this point q towards p, so this is another scenario for this one class. Okay, so for this kind of graph, as we move point q towards p, so we see that our x also moving towards x sub 0. So this is our limit x sub 0. Then our limit of the point q is point p. Okay, so we can say that in this scenario class, our slope, no, slope, that is the stiffness of our line, secant line, it tends towards negative infinity because it reaches the point of vertical tangency. These are point of vertical tangency. Okay, so we know that when it reaches, when this line, secant line approaches towards this line, so what will happen? So we have this negative infinity. Okay, now talking about differentiable and not differentiable. So this is the scenario class. If you look at this graph, okay, so if you trace this graph, say for example you have a point P here, and connecting these 2 points, so we have the secant line. And as you move the graph here and then closer to this point, okay, so we have the tangent line. For example, the point is here, so we have the secant line. So connecting these 2 points and this point, then you have the secant line. And as this point moves closer to point P, so it tends to this, it tends to approach point P. So we have this scenario class. So in this case, we say that uh, this function is differentiable at x equal to x sub 0. Alright, so differentiable at x sub 0. So this is our x sub 0 at this point. So our function is differentiable at x equal to x sub 0. So continuous. So whereas this one, so this is what we call not differentiable at x sub 0. Why? Because as the point q moves closer to p until it reaches p, so it reaches the point of vertical tangency. So it's no longer differentiable at x sub 0. And similar to this also, class. Okay, so it reaches the point of vertical tangency, this one. So not differentiable at x sub 0. Now we have here a theorem. Okay, so a theorem says that if a function f is differentiable at x sub 0, then f is continuous at x sub 0. Okay, so we have here some example, or one example of this. We speak of f continuous at x sub 0. This is one scenario class that shows us a continuous function. Okay, now we have here another definition. So using the same graph, but now our label is different. So here we have our point P has the coordinate for the horizontal component. We have x, meaning the distance from the y-axis towards that point P is x, and we can have the distance from the x-axis towards that point P is y. So therefore we have the coordinates of this point P as x and y. Alright, then we have this point Q here. So assuming that the horizontal distance, so we are considering the horizontal distance between point P and point Q, call it delta x. So therefore the the coordinate, the horizontal component of this point Q is x plus delta x, meaning the distance, this distance from the y-axis towards that point, we call it x. So the x here, class, is the same as x here. No? That is the distance from the y-axis towards this. So this is our x. Okay. Now the distance from the y-axis towards that this part here, this is just the sum of x and delta x. So that's why we have here x plus delta x. Okay. So if you just look at this, the difference of the horizontal components or horizontal distances, so you just subtract this one, then minus x. So what is left? This is the delta x. Okay. And similarly, the vertical distance from the x-axis towards point Q. So this is just the sum. If we call this one as delta y, delta y is the difference between the two vertical distances. Okay, so if this is because here that is the value, meaning the value of the function at this point, we have f sub x plus delta x, x plus delta x. So this is the vertical distance, class, from the x-axis towards this point Q. And this one is just f sub x, f of x. So when you subtract this distance from the x-axis towards that point Q, the distance is this one. Then the distance from x-axis towards that P, which is y equal to f of x, you just subtract the two. So this distance, the vertical distance of point Q, minus the vertical distance of point P. So we have here delta y equal to the difference of the two vertical distances. Now, if you are going to take the limit, of the ratio, so remember that in our previous discussion, I have a video posted just recently. This is what we call the rise. Okay, this is what we call the rise. I hope you can relate it, class, in our with our previous video. So we call it the rise. Okay, so consider this triangle here, right triangle, and this is what we call the run. Okay, so the delta x here is what we call the run. Now if you are going to take the ratio of the rise over run, so meaning the delta y, when you divide the delta y by the delta x, and when you take the limit of this ratio as the delta x approaches to 0, then what we have what we call the derivative of y with respect to x, or dy over dx. Okay, so this is our next definition, class, that the derivative of y with respect to x. So we have y here, the derivative of that's why we have dy dx. So that it means that the derivative of y with respect to x is equal to the limit of this ratio of the rise over run as delta x approaches to 0. Okay, and we can also say that the distance from the y-axis towards P as x, and the distance from the y-axis towards Q is w. So now if you take this difference, we have x, or sorry, w minus x, meaning the distance from here, from the y-axis towards this is w. Okay, so up to this point, this is w, and from here, this is our x, right? So if you are going to find the distance from this to there, okay, so this is this one, w, then minus x. Okay, so the difference of the two horizontal distances is w minus x. Similarly, for the vertical part, so we have Of course, this is our FW, no? This is our the height of this. So the height of this is from the x-axis. This is our FW. Okay, and then the height of P, this one here, which is also the same as this one here. So this is our f of x. Okay, so this is our f of x. So f of x. So you take difference. That's why we have here delta y is the difference. This is the difference of this height from the y-axis and this height. That's why we have here fw minus f sub x. Okay, so then we have here the derivative of the function x equal to the limit of this difference of the vertical component, which is what we call the rise, and divided by the difference of the horizontal distances, which is w minus x. So f prime of x equal to the limit of the difference of these vertical heights or vertical distances, which is what we call the rise, and the horizontal distances, which we call run. Okay, so don't be confused, class, for whatever we use, no, for the coordinates of our points. You just use the same concept as what we had discussed in the previous videos. Okay, now we have here another theorem that the derivative of a constant function is zero. That is, if c is any real number. No? So we have here the formula. So let's call this formula number 1. So this time, class, you have to list the formulas so that you have an idea of how much formulas that you are going to memorize. No? It's really very helpful when you memorize the formula. So the derivative of the constant with respect to x, so you read it as the derivative of the constant with respect to x equal to 0. So that's our formula number 1. So this is illustrated from this picture, class. So we have here a point. So we have the equation of this is, for this line, we have the horizontal line. The equation of this line is y equal to c. So y is a constant. It means that as the point moves, no, along this line, we can say that our value will remain constant. It will not change. So for example, if x, no, assume value x equal to 5. So when you find the slope of that, or you find the value of the slope of that, or derivative of that value, that is constant, no? So that's why we have here the value 0. So derivative of the constant is equal to 0. So it will never change. So along this line, if you have value of x equal to 5, so you see here the height will not change. So y is equal to constant. Now the derivative of that constant is equal to 0. So the tangent line to the graph of f of x equal to c. So this is the explanation, class. The tangent line to the graph of f of c equal of f of x equal to c has slope equal to 0 for all x. So if you can still remember from our analytic geometry, if you have our slope is defined as, we have y2 minus y1, right? If you can still remember this, y2 or y sub 2 minus y sub 1, and then divided by x sub 2 minus x sub 1. So the slope of the line is defined using the knowledge that we have in analytic geometry. So if you look at this, if you subtract the two vertical lines, so there's no difference. So that's why the difference is 0. So 0 divided by anything. Your x here could be any values, difference of two values of x's. Then your numerator is already 0. So 0 divided by any number that is equal to 0. So therefore your slope is equal to 0 as mentioned here. Slope 0 for all x. Whatever is the values of x, the value for y don't change. It's constant. So the difference of the ordinates is 0. So 0 divided by any number that is equal to 0. Okay, so that's the reason for that. Okay, so we have here another formula that if you take the derivative of x with respect to x is equal to 1. So we have here a graph represented by this line, this inclined line, where the relationship between x and y is that y is equal to x. So for every value of x, whatever is the value of x, that's also the value of y. So when x equal to 1, then y is equal to 1. When x equal to 2, y is equal to 2. So that's why as you move this point along this line, so you have corresponding values for x and y. So when you divide the x and y, so it will give you always a 1. So the slope is equal to 1 for this y equal to x. So graph equal to y equal to x. This is a straight line inclined or sloping towards the right. So the tangent line to the graph of f of x has slope 1 for all x. So the slope here is always equal to 1 for all values for x. Okay. Now another theorem. So again, class, this is just a review of what we had discussed before. So the power rule, it says that if n is a positive integer, then we have the derivative of x to the power n with respect to x is equal to n times x to the power n minus 1. So this is the power rule. Then we also have the extended power rule. So if r is any real number, then the derivative of x to the power r equal to r times x to the power r minus 1. In words, to differentiate a power function, so decrease the constant exponent by 1 and multiply the resulting power function by the original exponent. Okay, so that is how to read it in words. Okay. Now another one, we have what we call constant multiple rule. If f is differentiable at x and c is any real number, then c times f is also differentiable at x. And therefore, we have this formula that the derivative of the constant times the function of x with respect to x is equal to the constant multiplied by the derivative of the function of x with respect to x. Okay, that's the constant multiple rule. In words, a constant factor can be moved through a derivative sign. Okay? Anyway, class, we're just reviewing this part, so I'm a little bit faster or quicker at this time, as I've mentioned before. Okay, so another theorem, that is the sum and difference rules. So if the function f and another function g are differentiable at x, then so are f plus g and f minus g. And in summary, we have here the formula for the sum and difference of the functions. So derivative of the sum of f of x and g of x is equal to the derivative of f of x with respect to x plus the derivative of another function of x with respect to x. In other words, class, if you have the sum of functions, when you take the derivative of the sum, you just take the derivative of each of the function individually. Okay. Similarly, for the difference, if you have the derivative of the difference of two functions with respect to x, so you just take the derivative of each of the given functions. Okay, so that's the sum and difference rule. So in words, we can say that the derivative of a sum equals the sum of the derivatives, and the derivatives of a difference equals the difference of the derivatives. Okay, so if you find hard to memorize it this way, then you just memorize it in words. Okay, so while you are memorizing it, just to try to figure out how is it in mathematical expression. Okay, now the other one is the product rule. If the function f and another function g are differentiable at x, then so is the product f times g. And mathematically, we have this: the derivative of the product of the two functions f of x and g of x with respect to x is equal to f of x times the derivative of g sub x with respect to x plus g sub x times the derivative of f of x with respect to x. Or in formula, you can say that, or you can express this as uh, f times g. Then you have here the something above of this quantity equal to f times g prime, or this is read prime, no? F times g, or the quantity of f times g prime, equal to f times g prime plus g times f prime. Again, if you find it hard to memorize that way, then in words you can also memorize it this way: the derivative of a product of two functions is the first function times the derivative of the second plus the second function times the derivative of the first. So this is how to memorize it in words. Then while you're memorizing this in words class, try to figure out, no, mathematically. Okay, this way. Then the next one is the quotient rule. If the function f and the function g are both differentiable at x, and if g sub x is not equal to 0, then the ratio between f and g is differentiable at x. And the derivative of the rational function, or the ratio of the two functions f of x and g sub x with respect to x, is equal to g sub x times the derivative of f of x with respect to x minus f of x times the derivative of g sub x with respect to x divided by the square of g sub x, or can be expressed as f divided by g, or the f prime of f divided by g equal to g times f prime minus f times g prime over g squared. So it can be memorized easily by this way. Or if still difficult to memorize it this way, then memorize it in words. So in words, the derivative of a quotient of two functions is the denominator. Okay, so the denominator is this one, g sub x. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Okay, so memorize it that way. Now let us summarize. Let's have this table class that summarize the rules for differentiation. Okay, so the summary of differentiation rules. We have here the derivative of the constant with respect to x equal to 0. Okay, then we have the sum, the f, or the sum of f and g prime is equal to f prime plus g prime, and the product of f and g prime is equal to f times g prime plus g times f prime. And we have another scenario class, something like this, that if you have 1 over g prime, this is equivalent to the negative of g prime divided by g squared. Okay, remember this. This is very important. Then another one is that if you have cf prime, or the product of c and f then prime, equal to c times f prime. Okay, so this is a constant multiple rule. Then for the difference, we have f, or the quantity f minus g prime, equal to f prime minus g prime. Then for the quotient, we have f over g prime equal to g times f prime minus f times g prime divided by g squared. And we have the derivative of x to the power r with respect to x is equal to r times x to the power r minus 1. Alright, so far these are this is the summary of the differentiation rules. Then we have another formula here that you need to memorize also. We will give you details on this part later on, but now I want you to remember these two formulas. Derivative, this is trigonometric functions. The derivative of sine x with respect to x is equal to cosine x. So this will be our formula number 3. Okay, formula number 4, derivative of cosine x with respect to x is equal to minus sine x. Okay, now another one. Okay, let's just go on. Let's take the derivative of all the trigonometric functions. So for the tangent, so if you have derivative of tangent x with respect to x, this is equivalent to secant squared x. And if you have derivative of secant x with respect to x, this is equivalent to secant x times tangent x. So formula number 7, we have derivative cotangent x with respect to x equal to cosecant squared x. Formula number 8, derivative of cosecant x with respect to x equal to negative cosecant x times cotangent x. Okay, then we have the chain rule. So the chain rule says that if g is differentiable at x and f is differentiable at g sub x, then the composition is written as in this symbol, so meaning composite function. So the composition of f and g is differentiable at x. Moreover, if y equal to f sub g sub x and u equals g sub x, then y is a function of u, and the derivative of y with respect to x is just the product of the derivative of y with respect to u times the derivative of u with respect to x. So this is the theorem of our chain rule. Okay, so the derivative of f sub g sub x with respect to x is equal to this symbol. No? We have the composite function of f and g prime of x is equal to f prime of g sub x times g prime of x. Okay, so it seems that it's not easy to memorize it this way, class, or using this mathematical expression. So you can do it in words, no? Something like this, that the derivative of f sub g sub x is the derivative of the outside function. Okay, so outside function evaluated at the inside function times the derivative of the inside function. So what is the inside function? This one, right? The outside function is the f sub this. Okay? So we have here the generalized derivative formulas. Okay, so the derivative of u to the r equal to r times u to the r minus 1 times the derivative of u with respect to x. So take note, this is for the chain rule. Alright. Now if you have this sine function or the trigonometric function, so the derivative of sine u with respect to x is equal to cosine u times the derivative of u with respect to x. And for tangent, so derivative of tangent u with respect to x equal to secant squared u times the derivative of u with respect to x. For the secant, so derivative of secant u with respect to x is equal to secant u times tangent u times derivative of u with respect to x. So for cosine u, so derivative of cosine u, this is equivalent to negative sine u times the derivative of u with respect to x. For cotangent u, derivative of cotangent u with respect to x equal to the negative of cosecant squared u times du, or derivative of u with respect to x. And for cosecant u, derivative of cosecant u with respect to x equal to negative cosecant u times the cotangent u times the derivative of u with respect to x. Okay, so please memorize this one so that when we discuss this in details later on, it's easy for you to follow me. Okay, now we have here implicit differentiation. So another definition, we will say that if we'll say that a given function or given equation in x and y defines the function f implicitly if the graph of y equal to f of x coincides with a portion of the graph of the equation. So there are function class that where you cannot take the derivative uh, easily because of the way that the function is written. So in that way, if you're asked to, if in that scenario, if you're asked to find the derivative, so the only way to do it is to do it implicitly. Uh, so there are implicit functions. So we have another way of finding the derivative of that kind of functions. So later on, I will give you another video for that. So for now, just to give you some idea of what is this implicit functions. So for example, we have here equation x squared plus y squared equal to 1. So if you can still remember from our analytic geometry, this is a circle. So this is the representation of this function. This is a circle. Now, if you are going to solve for y in terms of x, so the only way is to transpose this part to the other side, then solve for y. So to solve for y, you take the square root on both sides. So that's why in our answer before, when you take square root on both sides, you have two values, plus and minus, right? So we have the square root of 1 minus x squared. That is the positive. So it means that this equation class represent the half part of that function, or in this case, our function is a circle. So that is what we call half circle. So the equation of that function is y equal to the square root of 1 minus x squared. This is half circle. The other one is the other half, which is the negative part of it. So we have y equal to minus square root of 1 minus x squared. Okay. So in fact, in our previous discussion, we called it, we have a function, a relation or not, right? So if this is the relation, is it a function or not? So we say not a function because if you do the vertical line test, it will the vertical line intersect at 2 points on the graph. So it's not a function. But if you have something like this, so this is now a function. Because if you draw a vertical line here, the vertical line will touch or intersect only at 1 point on the graph, similar to this one. Okay. Then for parabola, so this is an example of parabola, opens to the right. So it is given by this equation y, because parabola class, um, you have two values also when you solve for y. You have the positive values and the negative values. So when you solve for y in terms of x, so we have y equal to square root of x minus 1, and this represents the upper portion. So this half, no, semi-parabola. This is what we call semi-parabola. Okay, the blue one, and this is the tangent line to this point. Okay, similarly to this one, for the negative part of the parabola. Okay, so this is negative. This is also a semi-parabola. Okay, see, the semi-parabola is this is the function. But if you consider the whole thing, the whole part of this parabola, so this is not a function. Because if you drew the vertical line test, it will intersect at 2 points of the parabola. But if you consider only half of it, so we can consider it as a function and represented by this or this one for the lower part. Okay. Now later on we will talk about the application of the derivative. So We will be discussing about related rates. But before we talk about related rates, we will discuss about rate of change so that you can relate this video to the previous video that I had posted about 2 days ago. Okay, so when we reach that part, class, of our discussions, so I want you to remember this, no? When you are solving for problems on related rates. So these are the steps that you are going to use. No? Step number one, assign letters to all quantities that vary with time and any others that seems relevant to the problem. Then give a definition for each letter. Then step number two, identify the rates of change that are known and the rate of change that is to be found. Then interpret each rate as a derivative. Then the third step is find an equation that relates the variable whose rates of change were identified in step number two. Then to do this, it will often be helpful to draw an appropriately labeled figure that illustrates the relationship. Then number four, differentiate both sides of the equation obtained in step number three with respect to time to produce a relationship between the known rates of change and the unknown rate of change. Then after that, for step number five, after completing step number four, substitute all known values for the rates of change and the variables, and then solve for the unknown rate of change. Okay, so this is the strategy for solving related rate problems. Okay, so we have here parabola. So if you are going to use a magnifying glass, we have here different points here. So magnifying portion of the graph y equal to x squared plus 1. Okay, then we have here an example of a sine function. So this is our tangent line, y equal to x. Okay, then we have here in terms of differentials, so delta x, um, we equate this to dx. All right, so to relate this with our discussion on derivative, so our delta x is really equal to dx. Our delta y, we call it, we equate this to dy, where our dy is just part of the delta y. Okay, so the delta y is this one, this much, but our dy is just something like this. Okay, but if you look at the horizontal part, this is the run, dx is equal to x. Okay, so that's why we have here x plus delta x. So this time we will use x plus dx. Okay, we will also discuss in details this part, class, later on when we talk about differentials. Alright, so for the formula, derivative and differential formulas, so this is the summary. So just give you an idea, no, when we talk of differential later on. So this is how the formula is written in terms of differentials. So in the derivative formula, we have derivative of a constant with respect to x equal to 0. In differential formula, we have dc, meaning differential of the constant equal to 0. In constant multiple, we have derivative of c times f with respect to x equal to c times df, or derivative of the function with respect to x. Here we have the differential of c and f is equal to c times df. Okay, and so on and so forth. Alright, so you just explore this one, class, and perhaps with the use of these differential formulas, you can easily recall also how the derivative formulas are written. Okay, now we have here some question, but I'll give you this one later on when we talk about more on the applications of the derivative, class. Okay, so for now, I will stop this video up to this point. And if you have any question, you just comment or send your message in our group chat. Alright, so thank you very much. I will not make this very long because it's already too long. I know that you will get sleepy, when the video is too long. So I will stop up to this part, and see you again in the next coming videos. Okay, so thank you very much. Have a nice day. Keep safe and healthy always. God bless everyone. Bye.